Hi friends, today we are going to discuss about the equipotential surface. So what is meant by equipotential surface? So the potential throughout the surface is going to be equal potential, right? So first I am going to start with, so we have an electric field in this direction. So this is the electric field starts from here. So we have a uniform electric field in this direction. So when you are placing the surface here, which be something like this. If I place my surface something like this, so this is my electric field vector. So we have a area of cross section here, A. The normal of this area of cross section in the same direction. So listen. So if I place my area something like this is the direction of electric field. So now my normal of this area is parallel to my electric field, which means the direction, the distance from here to here is equal to distance from here to here, is equal to distance from here to here. So if I place my hand something like this, from this charge, what's happening? The distance is equal. So because my potential is directly proportional, inversely proportional to R. So from this charge configuration, though all the points in this, my point V1, point V2, point V3, so all the points, my potential is equal. So if the potential is equal, that's why it's called equipotential surface. If I rotate my hand something like this, what's happening? The distance from this charge to this point is not equal to this point to this charge. From the charge to this point. So here we have different potential, here we have different potential. If I place my hand something like this, the distance is equal. Here whatever the potential, the same potential will be here also. Now this surface is act as a equipotential surface. So equipotential surface is nothing but the potential throughout the surface is going to be equal. Okay. So if my potential throughout the surface is equal, what's happening? Say if I simply write my V1 equal to V2 equal to V3, so I can simply write my V1 equal to V2 equal to V3. The potential difference is 0, right? My potential difference is going to be 0. If my potential difference is 0, my work done is also going to be 0. If you want to bring a unit charge from here to here, if you want to move a charge from here to here, if you are moving a charge from one point to another point, the amount of work done is going to be 0. Since we have a potential equals to work done to bring a unit positive charge from one point to another point. If my potential, what does mean by potential? Is a difference between 2 points. V1 minus V2 equals to W by Q. So the potential difference between these 2 points 0 because V1 equal to V2. So is this 0 means my work done is also going to be 0. So in an equipotential surface, the amount of work done required to bring my charge from one point to another point is going to be 0. So this is my equipotential surface. Then when you are placing two same charges, or when you are placing a dipole in an equipotential surface, how it behaves. So in general, in the ordinary surface, my positive charge and negative charge is going to be attract. Why this is happening? Because my electric field starts from higher potential and end with low potential. But in the case of equipotential surface, my electric field is not flowing from higher to lower because all the surface is going to be equal potential. So this is very, very important question in the exam point of view and the competitive exam point of view also. So when you are placing a dipole in an equipotential surface, so in an equipotential surface, so if I have my negative charge here and we have a positive charge here. So these two charges are going to repel each other. So this is not going to attract. This is not going to attract. It is going to be repel each other. In the ordinary surface, positive and negative charges are going to be attract, but in the equipotential surface, my positive charges and negative charges are not going to be attract because there is no potential difference. If there is a potential difference, the electric field starts from positive and ends with negative, then it is going to be attractive force. But here my dipole in an equipotential surface, there is no attraction at all. So if I have a two positive charges, what's happening? if I have two positive charges in an equipotential surface, this is going to be attract each other. Okay, if I place two negative charges in an equipotential surface, this is also going to attract each other. So when you are placing like charges in an equipotential surface, it's going to be attract. If you are placing the unlike charges in the equipotential surface, it's going to be repel. This is because of the potential difference is potential difference is 0. Potential throughout the surface is going to be uniform, right? Next, if I have a point charge, how can we construct a potential equipotential surface? So if you are sitting in the center of the football, so for example, if I place a charge inside the football, center of the football, so with respect to the center of the football, my electric field is always going outwards in all directions. So the surface is always parallel to your electric field. The normal of the surface is always parallel to the electric field. So the surface of the football is act as a uniform or equipotential surface. So for example, if I suppose to consider a positive charge here, I am considering this. Actually, if it is a uniform, the radius is going to be r. If it is uniform sphere, okay, if it is a sphere. So my electric field is going in all direction. So the normal of this surface is also the same direction. When my normal of the surface is parallel to my direction of electric field, so this surface is act as a equipotential surface. So this is very, very important concept. So next, in the exam point of view, the last this kind of questions I will explain the here, but here they give example here. So we have a charge here. Either we don't know the charge, we have to find the charge. So we have an equipotential surface. This is my Q here. So this is going to be 9 volt. This is going to be 8 volt. This is going to be 7 volt. Listen carefully. We have a charge Q here. We just want to find whether it is a positive charge or negative charge. So listen carefully. This is one equipotential surface with a high potential. This is another equipotential surface. The potential throughout this surface is going to be same. The potential throughout this outer sphere is going to be 7 volt, is same. But this potential is not equal to this potential, is not equal to this potential, because from the charge Q, the distance is variable. So each sphere is act as a separate equipotential surface. Now how can we find the charge, whether it is a positive charge or negative charge? Simple logic. When my potential is decreases, what's happening? My electric field is going outwards. So my electric field is always travel from high potential to low potential. So the charge inside the sphere, spherical shell is going to be positive. So since it's a positive charge, my electric field is going outwards. So it's going towards the low potential. That's why it's negative. If I have a negative charge here, negative Q here. Okay, so this is my 7 volt, and this is going to be 8 volt, and this is going to be 9 volt, because my electric field is coming from infinity to the negative charge. So this is my higher potential, this is near to the positive charge, this is near to the positive charge, and this is away from the positive charge. So this is going to be 9 volt. So in the examination, they are asking you to find what is the charge, either it is a positive charge or negative charge. Find the direction of the charge, they will ask. So these kind of questions coming in the HOTS type. Okay, so that's it with the equipotential surface. Next we are going to obtain the relationship between electric field and potential. Okay, relation between electric field and potential, right? So if I have my positive charge here, so this is the direction of the electric field, right? So for example, so if I have my positive charge here, so this is the direction of the electric field. If I place my hand something like this, the distance from the positive charge, the distance is same. So this surface is act as a equipotential surface. If I place another hand here, so this hand is also, this plane is also act as a equipotential surface, but this potential is not equal to this potential. So this is act as a separate equipotential surface, this is act as a separate equipotential surface. So now we have a two equipotential surface. So one equipotential surface be here, is said to be A, plate A with potential V. We have another equipotential surface B plus delta V. So this is my plate B. So the separation between the plates is said to be delta L, okay, or dV or dL, doesn't matter, it's a small change in my potential. So this is act as a one equipotential surface, it be something like this is act as another equipotential surface, but this potential is not equal to this potential. So we have a two equipotential surface with the different potentials. So now what I am going to do here, I just want to bring, actually I am going to take this as my capital Q. So I just want to bring a unit positive charge Q from plate 2 to plate B to A. So if you want to bring from here to here, you need not to do any work, because my positive charge is going to be repel this guy, then this move away. But this means is a positive charge and this is also a positive charge, it is going to be repel. So we have to do work against the electrostatic repulsion. So this positive charge is going to be repel this guy. So now my work done required to bring my unit positive charge 1 coulomb from here to here. So I can simply write the work done to bring plus Q from B to A. I can simply write my work done equals to, it's a potential difference between 2 points. Since W is equals to Q into V, anyway my Q is going to be 1, so my W equals to V. So V is nothing but my potential difference between these two limits. So potential VA, final minus initial. Okay, this is my final, this is my initial. So VA equal to V, VB equals to minus of B plus delta V. So you can simply cancel these two, I can simply write minus of delta V. This is my to get my work done. So my work done is nothing but minus of delta V. So the change in the difference in the potential only decides the work done. Okay, so it's just not depending upon this V. Next, I am going to write the expression from the Newton's law. So simple logic, or from the electrostatics, actually not from Newton's law, from the electrostatics. So I can simply write the work done, W is equals to force into displacement, right? My force F equals to Q into E. Anyway, Q is going to be 1, so F is equal to E. Then I can simply write modulus of E into delta L. Okay, so I can simply write this is my equation 2. So now this is work done from the electrostatics, this is the work done from the potential difference. So if I equate these two, equation 1 equals to equation 2, then I may write modulus of E into delta L equals to minus of delta V. So therefore mod of E equals to minus of delta V by delta L. So my electric field is nothing but the negative gradient of the electric potential. So my electric field is the negative gradient of the potential. My delta L varies, the potential also will change. So why this is minus sign? This minus sign, in the electric field direction, the potential decreases steepest. So if you want to bring my charge from A to B, the work done is going to 0. But if you are moving against, because I am moving my charge from B to A, we are doing work against this electrostatic repulsion. That's why my electric field in the negative gradient of the potential. What is meant by gradient? A quantity varies with respect to length or distance is called gradient. So in this case, my electric field decreases steepest in the direction of the, so my electric potential decreases steepest in the direction of the electric field. So this is the relationship between the electric field and the potential. So I just stop at this point. If you like this video, share it with your friends and subscribe our channel to get the more content. So thanks for watching. We'll meet the another video. Thank you.